In this video, we are focused on system properties. In general, we have 6 properties we're going to focus on, and we're going to go through each one of them individually as later in this discussion. and it's really important to have the exact definition for each property, and then when we're trying to decide whether the system is applying those properties or has those properties or not, really always go back to that short description or short definition of what the property is. Before we go too far, throughout this document, when we are talking about the continuous time, we are talking about a system that the input is x of t and the output of the system is y of t. Okay? And when we're talking about discrete time systems, we are assuming that x of n is the input and y of n is the output. Okay? So, and then we're going to, as we describe the system properties, I'll try to alternate back and forth between continuous time and discrete time examples, but they are fundamentally very, very similar to each other. So let's go ahead and start with the definition of a memoryless system. That's property number 1 that we're going to cover here. So in a memoryless system, output only depends on present input. Okay, so what are the simplest systems you could have? Well, the simplest system, of course, would be y of n or y of t equals to x of n. Well, the output only depends on present input. So how about this one? How about if the system was y of n equal to x to the power of 4n plus log of x of n, or some other crazy function we can put in here? The answer is this is also a memoryless system because it does only depend on the present input. Notice the x of n, that's a present input. So let's go ahead and kind of go to the next and see. So then what does a memoried system look like? Well, here is a let's say one of the simplest one we can write is y is equal to x n plus 1, right? Well, now the output depends on presence and future x, which means this is actually memoried. Or we could have been doing a lot of discrete, so let's do a continuous time. So how about this one? This is, of course, memoried system also because it depends on past input. So you always go back to the definition, okay? And then for kind of extra credit off of, I suppose, how about this one? Y of t equal to e t plus 5 x of t plus t minus 2 times x of t squared. So you notice we got t plus 5 and t minus 1, but none of these are shifted the input. Y of t still depends only on present state, so this one is memoryless as well. Okay. So that's basically the property of memoryless system versus memoried system, property number 1. Let's go ahead and take a look at property number 2. Property number 2, the definition says invertible, whether the system is invertible or not invertible. A system is invertible if the system generates unique output in response to a unique input. So what they're basically saying that for every value of input, whether it's x of t or x of n there is only one possible y of n, or correspondingly one y of t. There can be multiple possibilities or not being able to achieve the answer. For example, if I say y of t is equal to 5x of t, there is no ambiguity that if x is given at 2, what y is, or if y is given at 2, what is x is. There's just a one-to-one correspondent. Therefore, this is indeed an invertible system. Let's take one that may not be. So for that, I'll take a look at a discrete one just to have another example. How about, and I have a problem here because, so let's say someone tells us y of n is 25. Okay, if y of n is 25, what are the possibilities for x of n? X of n potentially could have been 5 or minus 5. Therefore, this system is not invertible because I can't go back for every unique input. There is not a unique output or vice versa. So that is a failure in the system. Or not a failure, but it's a non-invertible system that I'm working with. So, okay. So what is causality? Causality is a little bit of an interesting animal. Let's go ahead and look at this property and read about it. A system is causal if the output depend only on present input and past input. So if you want to have a causal system, you cannot have an output depend on a future input, right? Output should depend on causal. Most of the natural systems are causal, where they depend on the present and past input to indicate what the output of the system is. Now, if they're non-causal, they're more predictive type systems. So let's go ahead and take a look at this. So for example, if I have y of n is equal to 5x of n plus 5x of minus n minus 5, is this causal or isn't it causal? Well, if you look at this thing, you'll say, okay, y of n, that's n is the present, it depends on the present input, and n minus 5, which is a past input. So this is indeed causal. Okay, now let's take a look at another one. So what happens if I just go in here and change one thing? I say this is dependent on 5x of n plus 5. All of a sudden now my system is not causal or non-causal because I'm depending on the future input. Because if n is equal to, let's say, 1, I'm depending on x of 6, which is in the future. So this would be a non-causal system. Or so let's take, this is the one that kind of deceives a little bit. So if I write a y of t equal to t plus 5, e to the t minus 4, and then x of n minus 2. Is this thing causal or not? You do not want to be distracted by t plus 5 because t plus 5 has nothing to do with the input. That's just some time multiplied by some other constant. You need to look at here to see if my, should be a t, not an n, t minus 2. You need to look in here and see if it's depending on the future or past input. This is past input, therefore this is a causal system. The next one is called stable. Next property, system property, is called stability. And stability basically is a stable system is one which finite input leads to finite output. In other words, you cannot put a finite input in and get an infinite output. If that happens, you don't have a stable system. So a finite input should give you a non-infinite or finite output. So let's take a look at it. So let's say I have y of t equal to 2 to the power of 200 and cosine of 225 pi t times x of t minus 5, let's say. Well, you look at this and say, is there any way that I can put a finite input in here and I get an infinite output? There's no way, because cosine, the maximum minimum of cosine, ranges from -1 to less than or equal -1 to less than or equal, larger or equal to -1 and less than or equal to +1. So, and then this is, yes, is a big number, but it still is a finite number. And if so, if this is a finite number, the y of t is always finite. Therefore, this is a stable system. So if you ask, so what does an unstable system look like? Well, if I take a look at y of t is equal to t x of t, something really simple. There you go. So, well, yes, this is finite value I'm putting in, but what if t is infinite? Then the output is infinite. So this is a non-stable system. Okay. Another example potentially could be y of n is equal to 2 to the power of n, x of n minus 6. Well, this could be non-finite, but n could go to infinity, which means that can go to infinity. So that's, again, not non-stable. Okay. Time variance is kind of interesting in that it's basically saying my system will behave the same whether I'm using it now or I'm using it sometime later. And the way we think of this is that the best way to think of that is, if I take my x of t and I put it in my system and I get y of t, okay, and then let's say y1 of t, and then I shift this thing by t0, I will get y1 t minus t0. Then I'm going to take x of t minus t0 and I'm going to put it in my system, and the output I'm going to get, it's basically the system is sitting here, okay, and I'm going to get y of y2 of t, let's say, that shift, this is shifted, input is shifted, I get y2. This one, I don't shift the input, but I put it in and shifted, I get this. So these have to be the same. If they are the same, then the system is in time invariant or variance. If otherwise, it's time variance. So let's take a crack at some. So let's say I have a system. It's let's say y of t is equal to 25 x of t for the time being. And you say, okay, fine. So first rule is I'm going to shift this to get that y1 of t minus t0, and that would be equal to 25 x of t minus t0, because everywhere I have t, I have to replace it with that. And then what I'm going to do, I'm going to shift x of t to x of t minus 1 and plug it in. If I do that, then y of t, or let's call it y2 of t, is going to be equal to 25 x of t minus t0. Well, these are exactly the same, so the system is indeed time invariant. Now, how could I make that this similar system time invariant? Relatively easy. All I have to do is, if I take the t out, then I've got the same system, similar system, but this is time variant, because if I shift this thing, I'll get y1 of t. y1 of t is equal to t minus t0, shifting it by t0 is 5 of t minus t0 times x of t minus t0. Now if I take x of t and shift it, so I have this, and I put it in the system, now I gotta go to y2 of t, and that will be 25t x of t minus t0. So these are not equal, therefore this is not time invariant. So that's a double negative, so it's time variant. Okay, so finally we get to the last one, which is called linearity. Linearity basically says that if a system is linear, then superposition works. In other words, what that means is that if I've got y 1 of t I get that in response to x1 of t. I put my x1 of t in the system and I get y1 of t. I put x2, another input of t, and then I get y2 of t. Then I'm going to take both of these together, x1 of t, and I'm going to add x2 of t to it, and I'm going to put both of them together through the system, and I'll get y3 of t. Okay? A system is linear. System is linear if y1 of t plus y2 of t is equal to y3 of t. That is the linearity. And if you remember, we've used this property before when we were doing our superposition and in the circuit analysis side. So what basically this is saying, look, if I put one input in, I get y1. I put this another input in, get y2 individually. Then if I put them together, I get an output. But that output is the same as if I added the first two. And that's the definition of linearity. Okay. So let's take a look at some functions. So let's say if I have y of t equal to 25t squared x of t, let's say. Is that linear or not? Well, you look at t squared and say, maybe not linear because it's got a t squared. But remember, we are looking at linearity for a relationship between x of t and y of t. T and t squared has really no bearing on anything, because if I do the test, I'm going to put x1 of t in the system, which means y1 of t will be 25t squared x1 of t. And if I put x2 of t in there, then I've got y1 of t equal to 25t squared plus x2 of t. Oh, so t squared, and this is t squared x2 of t. Now, if I put both inputs in at the same time, then I get y3 of t, which is going to be equal to 25t squared times x1 of t plus x2 of t. As you can see from here, we can say that y1 of t, and this should be y2 actually, y1 of t plus y2 of t is indeed equal to y3 of t, therefore the system is linear. Okay? Now, what would break linearity? Well, the simple one is just like every other math question. It would be if I had xt squared. This is clearly not linear. Just because if I put the inputs in there, it won't work. So that's an example of that. That brings us to the end of the properties. So if you remember, we've talked about 6 system properties. One was memoryless, or memory. The second one we covered had to do with, I forgot what was the second one, so we'll just go look at it. So invertibility. Can you get a unique output for every input that you have, or vice versa? That's called invertibility. The next one is causality. Causality basically told us that you can't, if the input depends only on past and present, then it's causal. Then we had stability. Finite input causes finite output. We had time invariant. Doesn't matter whether I put something in today or I put something in next day. Next day I get the same output. The system behavior doesn't change. And finally, the linearity exhibits superposition properties. That brings us to the end of these 6 system properties.